Math distance learning class. Today I have got a very interesting and a very important video for all my grade 11 and 12 students. So in continuation to the last video that was uploaded on my channel, I have today for you another part 2 of the topic of differentiating inverse functions. So let's get started. So in the session today, we are going to be focusing on solving problems on differentiating various inverse functions. And as I told you, this is a must-watch video for all my grade 11 and 12 students. It's a very important question which is generally asked for all your examinations. So watch the video till the end, look at the problems that we discuss, and then answer the question towards the end of the video. Let me tell you the learning objectives for today's session. So in the session today, we will learn about the method to find the derivative of inverse functions, and then we'll be solving some important problems on derivatives of inverse functions. So let's get to the first question now. Start solving example 1 with me. I would advise you to have a watch at my last video, which was giving you an introduction of inverse functions. I will put the link in the description box, and I would recommend you to watch that video before you move on ahead with this video. Okay, so I'll read the question for you. In example 1, we are verifying whether the given two functions fx and gx are inverse of each other or not. So what we are going to be doing, we are going to be first checking for the domain and the range of both the functions f and g. And here it's quite obvious that both of them have the domain and the range as real numbers. So we can conclude that the composite function f of g is going to exist for all x. So let's first find the composite function f of gx, that is f of gx. And then later in the question, we'll find the other composite function, which is g of fx. Okay, so when I'm trying to find here f of gx, that means in function fx, we take input or inside the value of the function gx. So when we substitute gx in place of x in the function fx, what we get is the composite function f of gx. So what we are going to be doing, we'll go to our function fx, and wherever there is x, we are going to replace it with the function gx. So when we do substitution of gx in fx, what we get is this function. So that is 2 times cube root of x plus 1 divided by 2 minus 1. Now there is cube root inside the bracket and you are taking cube outside. So both are going to cancel and you will be just left with 2 times x plus 1 divided by 2 minus 1. So this cube root, this radical sign will go away. Now your 2 and 2 can cancel, and x plus 1 minus 1 is going to give you an x here. So the one part of the composite function f of gx is x here. Let's check for the other part also. Before we calculate the other part of the composition, I would want you to recall from the previous class, from the previous video, the definition of an inverse function. So how are you going to verify? The two functions f and f prime are going to be inverse. Remember, this is coming from the definition, very important. If and only if the result of the composite function and its inverse in either order is the original input. That means what we are going to check, the condition that we are going to verify is that f of gx, this composite function, and the other composite function g of fx that we will very shortly find is going to be equal to the original input x. So if this condition is true, very well we could say that f and g are inverse function. So let's check for gx, the other composite function g of fx here. And here definitely you will first take the function g, and inside you will take the input as the function fx. So let's substitute in function g the value of fx. So when you do that, you are getting cube root of 2x cube minus 1 plus 1 divided by 2. So plus and minus 1 are going to cancel. You can simplify and cancel the 2, and that would give you, after cancellation, cube root of x cube and further you simplify, that would give you x again. So what we have seen here, that this condition has been very true for us, that both f of gx and g of fx have come out to be equal to the original input function x. So wonderful, that condition we have checked nicely for this question. Okay, so we have concluded till now in the question that f of gx and g of fx both are going to be equal to x, and hence we have concluded that both are going to be inverse of each other. Now I want you to have a look at the graph of these two functions. So let me just highlight in this image that you see here. First, we have drawn the graph of the function fx, which is 2x cubed minus 1. So it is this black line that you see. And then we have drawn the graph of gx, which is the inverse function cube root of x plus 1 divided by 2. That's this gray function. And finally, now you're going to draw the line y equal to x, this dotted pink line in between. And I'm sure looking at the graph, you have really observed that the graph of f and its inverse g are mirror images of each other with respect to this line y equal to x. Or you can say y equal to x is acting as a mirror for the graph and its inverse. So what we can conclude from the graph is that the graph of f inverse is a reflection of the graph of f through the line y equal to x. So this is a very, very important observation that would lead you to an important property talking about the inverse of a given function. That brings us the last question to the key concept 1, which is called reflective property of inverse functions. So let me summarize this property for you. The graph of f contains the point a, b if and only if the graph of f inverse contains the point b, a. So this is a very important theorem, a very important relationship, and it would really help you, this reflective property of inverse function, to solve questions. In the slides to come, you will be able to see how you will be using this property. And here the important part is that the graph of the two functions fx and its inverse are the mirror images of each other when they pass through this line y equal to x. So y equal to x is just acting like a mirror for these two graphs. Okay, so let's take this another example that will explain the reflective property nicely. So here what you can see are the two graphs of f and f inverse. So the function fx is defined as x cubed minus 2. So you can see the graph of this function as this part. Now across the y equal to x, which is the mirror image, you will have the graph of the inverse. So this graph, the second graph that you see, is the graph of f inverse of x, and this was for fx. Yeah. So what is the theorem saying? What is the theorem conveying to us? So the theorem says that if you have any point, for example at this point you are having the slope of the graph as 12, you can see that very well by calculating the derivative, and the point that you have taken is 2, 6. So the image of this point for the function fx, which corresponds to the function f inverse x, is 6, 2. So what you have done, you have just flipped your x and y coordinate, and therefore we could say that the derivative of fx at the point 2, 6 tells us the derivative of f inverse at the point 6, 2. Now let's see another example that will help you to apply the theorem that you've seen in today's lesson. So the example says if f of 3 is given to you as 8, so I will highlight the values, and f prime of 3, that is the derivative, is given as 5, what do you know about the inverse? Yeah, so these two values are given. So because it is given that f of 3 is 8, so can we say that 3, 8 is going to be one point that will lie on the graph of the function fx? Yeah, so you've got 1 point. Also you are given the derivative, and I hope you remember that derivative gives you the slope of the function. So this is actually the slope of fx at the point x equal to 3, that is given to you as 5. Now using the last theorem, you know that if the function is going to pass through a comma b, then the inverse should pass through b comma a. So that means f inverse, if you just flip the two coordinates x and y, must pass through the point 8 comma 3. Also the slope of the function for the graph of f at the point 3 comma 8 was 5 because the derivative was given here. Therefore the graph of f inverse must have the slope which is again the reciprocal, that is 1 comma 5 at this point. So that is your example 2. The important observation that you saw in the last question brings us to this key concept 2. Now this key concept of 2 is known by a theorem called as the derivative of the inverse function. So what does it say? Let's try and understand. If f is a function that is differentiable on an interval I and it has an inverse function g, then g is said to be differentiable at any x for which f prime of gx is not equal to 0. So this function, which is giving you the derivative of the inverse g prime, has to be well defined so that the denominator is non-zero, and then g prime of x or the derivative of the inverse function is equal to the reciprocal of the derivative of f at the point gx. So you could read it in this way, that the derivative of the inverse function at a point is the reciprocal of the derivative of the function at the corresponding point. So remember, if the point is a comma b for the function, then it would correspond to the point b comma a for the inverse. Yeah, and similarly their slopes, the slope of the function given function f and its inverse function g are going to be reciprocal. So these two important key concept you should remember, and again you would see that in the slides to come how we can apply these two results for the derivative of the inverse function and the slope of the line of tangent to f inverse in solving problems on derivative of the inverse. Remember this key concept, and let's see some examples now. Let's solve the last problem for today, which is example 3 based on the last theorem that we have seen. So we are going to be using the property that f inverse, its derivative at point x, is going to be the reciprocal of f derivative of the inverse. Okay, so we are given here the function fx, that is x cubed minus 2, and we need to find the derivative of the inverse function g at the point 6. So let's use the information which is given to get the derivative of f, that is f prime of x, that is going to be equal to 3x squared. So we have just taken power rule here, and negative 2 being a constant, the derivative is going to be 0. Now we need the inverse of this given function fx. So you can use the method that I had taught you in the last video, that was part 1 of inverse function, to get your inverse function gx as cube root of x plus 2. Now the point at which we need the derivative is 6. So we are going to substitute here in place of x 6 to get our value. So that is cube root of 6 plus 2 or cube root of 8, which is equal to 2. So g of 2 we have got. Now we need g prime at the point 6. So if we use the theorem that we have seen in the last slide, then this is going to be inverse reciprocal 1 over f prime of 2. Now why this has happened? Because g and 2 are your inverse points. So just substitute in place of g of 6 value 2. So it is coming from here. Yeah, so if I just add on one more step to make it clear, f inverse derivative at the point 6 is going to 1 over f prime of g at 6. So this is how you have applied this important formula, and then you have replaced your f inverse with g and g of 6 with 2. So 1 over f prime of 2. You know f prime is 3x square. So to get f prime of 2, you just substitute x as 2 and that gives you 1 over 12. So that is your answer. And if you want, you may just use Desmos to get the graph also. You will be able to see the companion associated corresponding point, and that can also be used for solving this question. So that is all about derivative of inverse functions for today. We have covered some important questions. Please revise today's session and looking forward to you meeting all in the next session. That is going to be again for grade 11, and the topic that we are going to be doing in the next video would be your implicit functions part 2. So that's all for the session. Thank you so much for joining, my dear viewers, and don't forget to like, share and subscribe to my channel Mathematics Made Easy. Until next time, see you in the next video. Bye bye.